All right, we are live to tape. So once again, good morning to you all, and welcome to the third and final section of this course. We've passed through now two sections in which we've done quite a bit of reading and discussion, and we're about to enter the third, which is titled Puzzles and Paradoxes. It's kind of fun, in a way, at least for philosophers, because we spend a lot of time dealing with such things. And I guarantee that this will be both fun and challenging for you. I've, over the years, learned that students generally enjoy this section very much because it presents, on the one hand, some abstract problems that are real mind teasers. So get ready to have your minds twisted into several kinds of pretzels in this section of the course, but also some of the puzzles that we're going to look at turn out to have tremendous and important applications for everyday life, perhaps surprisingly. But we're going to, especially when we get to the prisoner's dilemma in a few weeks, we'll see that it applies to all kinds of real-life situations. So on the one hand, we're looking at puzzles that have very interesting conceptual facets, and which philosophers have discussed for hundreds of years, in some cases thousands of years, but also which have some real traction in our everyday lives and decisions that we make. So I hope you'll enjoy this section of the course. And before we launch into Zeno's paradoxes, which are the subjects of this week's lectures, I just want to say one thing to you about last week and our discussion of John Stuart Mill. Last week, for a variety of reasons, I was the absent-minded professor, and I know that I ended the Monday plenary a little bit earlier than anticipated, because I basically got the times mixed up. Well, and in the process, we were embarked on a very interesting and important discussion about free speech, freedom of expression in general, and how one could, in fact, prevent having one's mind taken over by somebody else. In other words, losing what John Stuart Mill called the sovereignty of one's own mind and body. But we were talking about minds, and I think Randy in particular was asking some very good questions, and some of you were chiming in because these issues are very relevant to us today. So let me just say to you that I don't want to abandon that. And on our last day of classes, which is May the 17th, I make that a Monday, I want to reopen that discussion, all right? So I'll just say to you that we're going to cover in this third section the material that's in the syllabus this week. It's Xenos Paradoxes. Next week, it's Anselm's ontological argument, which is actually a very clever, the most clever proof ever devised for the existence of God. The third week, we're going to look at the prisoner's dilemma, which has many, many facets to it. Very interesting and challenging dilemma. In the fourth week, we'll be looking at Newcomb's problem, which is really a kind of a variation on the prisoner's dilemma, a very fascinating one. But then the last lecture, that will be on Monday, May 17th. I want to review any questions that you will want to raise about the paradoxes and puzzles, but also reserve some time for further discussion about freedom of expression. All right? So that's our roadmap going forward from here to the end of the course. And I just wanted to say one thing that I would have said had we spent more time last Monday, just some food for thought, that it is very much a danger to our own sovereignty of mind when we are exposed to incessant propaganda. And this is certainly one way in which governments can actually kind of take possession of people's minds without them even realizing it. One of the most insidious facets of propaganda is that people who are thoroughly propagandized don't realize that they're propagandized. It's a bit like operant conditioning. And so there's a great danger because people who are propagandized are no longer free to think for themselves, as Mill wanted us to be, and are, of course, no longer free to express themselves because the state may simply shut down any freedom of expression. And we have seen this historically in recent memory and in recent history. Of course, the Nazis would have killed anybody who disagreed with them publicly. They totally shut down and censored freedom of expression. So did the communists in Russia. The Soviet government allowed no freedom of expression at all. The Chinese Communist Party does not allow freedom of expression. And neither does the American radical left, and neither do the technology platforms that are allied with them. Facebook, Twitter, and Google do not allow freedom of expression either. Any opinions which run contrary to the narrative that they want to basically instill in everybody are simply censored. And that's a great danger. So if you are told every day, incessantly on every channel, radio, television, and mainstream, internet. If you're told the sky is green from the time you wake up in the morning to the time you go to bed at night, and if you're told for 5 years every day that the sky is green, the sky is green, the sky is green, you're going to start believing that the sky is green. And this is one of the most insidious effects of relentless propagandization, that even when you look up at the sky and see that the sky is blue, just because you have been propagandized relentlessly, you're going to start disbelieving your own eyes. And you're going to start believing that the sky is green. And then if anybody says the sky is blue, they're going to be taken for a heretic and punished and censored. So this is one of the dangers. And that this was really to Randy's question. This is how our minds can be harmed without our consent. Normally, we want to form our own opinions. And if we have truly a free society, where we have open discussion of every single issue, as Mill wanted us to have, where nothing is forbidden, nothing is taboo, there is no book we cannot read, and there is no topic we cannot address, only then, in such a climate which is truly inclusive and diverse, can we have freedom of expression, and can dissenting views be heard, can all views be heard, and therefore we walk away with our freedom to form our own opinions, but always with the tolerance to hear views that may be different from our own. And that is the kind of freedom that was advocated for a long time in democratic societies, and which I believe furthered scientific progress, furthered social progress, political progress, and so forth. When those freedoms start to get shut down, we run a great risk of becoming just like the totalitarians against whom we fought for so long and paid such a dear price to triumph over. So that's my political sermon for this morning. I will now stop, but I wanted to say that to you on Monday because the questions were so important, and we will return to this. And I will welcome any points of view and all points of view that people want to bring to that discussion. So please reserve it for May 17th, Monday morning. Mark your calendars, and we will have I hope, a very fruitful interaction of opinion. Okay? And that will be a fitting note on which to close our course. So, okay, I'm glad you got that, Randy, and others. All right, so now let's put the politics aside for a moment and the propaganda aside for a moment, and let us return to some very interesting philosophy. Okay, everybody take a deep breath. Is that all right? Are we back on the same page now? Okay. You're all silent. All right, maybe I hit you a little too hard this morning with some very important stuff. Okay, Renee's all right with it. Reyes, okay. I'm seeing some yeses in the room. All right. As long as you're okay with this, now we're going to come back to the syllabus and tackle paradoxes and puzzles. Okay, let me ask you a question. This is a question which leads us into the material for this morning. What is the difference between a dilemma and a paradox? Can anybody enter in the chat room an answer to what is a dilemma? For example, what is a dilemma? That's a question because we're going to be looking at some. And on the other hand, what is a paradox? They're not the same thing. So we need to be clear about the basic terminology and what it signifies before we start tackling these examples. So we use these words quite regularly in everyday speech. People always talk about having a dilemma. Paradox a little less used in common speech, but I'm sure you've heard the word. A dilemma cannot be solved. A paradox arises from a flaw and can be solved. Very good, Denise. I think that's a tremendously astute characterization, and I'm going to elaborate on it. So good for you that you know this. Everyone else is going to know this in a few minutes. Randy says a situation that has two difficult choices is a dilemma. Yeah, it comes from the Greek. The Greek prefix is dilemma, meaning a double-edged sword. And we have to choose one, but we don't really necessarily know which one to choose. And basically, in a dilemma, you're forced to make a choice, but you really are not sure which of the two choices is going to be the better one, because in a dilemma, both choices will appear to have perhaps advantages, but definitely disadvantages. And that's why in English, maybe some of you have heard the expression being on the horns of a dilemma. Yeah, we talk about the horns of a dilemma because the horns are like a bull's horns. When you're on the horns of a dilemma, it means basically you're going to impale yourself on one or the other. And you really don't know which horn you'd rather be impaled on. But in a certain sense, in a dilemma, neither choice is really apparently a perfect or at least an acceptable choice. So you have to try and navigate that. But you're going to choose ultimately which horn to impale yourself on, meaning that neither choice is really good, and maybe something bad will happen. But even if you want to do the least worst thing, it's not always clear which choice that is. All right? So that's a dilemma. And we face dilemmas, on a regular basis. Paradox, as Denise has said, arises from a flaw and can be solved. Yeah, a dilemma can't be solved in the sense that there's obviously going to be one choice that emerges as a superior to the other. So a dilemma is always going to entail kind of rolling the dice at some point, or at least taking a chance on one or the other of the choices. So a dilemma by definition is not resolvable. But a paradox is, that's quite correct. A paradox, and I'm going to show you a slide in a moment that will define a paradox a little bit more closely. Let me just share that with you. I have it prepared like a cooking show. I prepared something in advance, and I'm going to give you some examples of paradoxes, because we're looking this morning at a couple of very famous paradoxes from the ancient Greek Zeno, or Zeno, depending how you want to pronounce him. So let's first see in general what a paradox is, and then we'll look at a few examples of different kinds of paradoxes. And finally, we will actually start tackling Zeno's paradoxes themselves. So here is a slide. Can you all now see this slide on paradoxes?
Yes.
Yes, okay, thank you. So it's two slides, actually. The first one is called Paradox, and I've spent a lot of time on these, or maybe some people would say wasted a lot of time. Philosophers like paradoxes, and we devote quite a bit of our time. It's the kind of thing that makes us lay awake at night, thinking how to resolve a given paradox. History's full of them. And there are many kinds. There are logical paradoxes, semantic paradoxes, computational paradoxes, empirical paradoxes, set theoretic paradoxes. There are whole families of paradoxes. Some of them have been resolved, others have not, and others are still in a gray area where people claim to have resolved them, but then other people disagree about whether the resolutions in fact are sound or not. So the subject of paradox is eternally fascinating for us. Maybe you've never thought too much about these things, but I guarantee you this morning you're going to be thinking about them. So in general, the most general way to understand what a paradox is to define it as, this is my own wording, a paradox is an argument or deduction that leads from apparently rational or logical premises to a seemingly impossible, in other words, paradoxical conclusion. So we give some kind of an argument, and it seems to be at every step of the way rational, so each step seems to be correct, but then the conclusion of the argument will appear to be absurd or impossible or crazy. So we say, well, how do we get there? Because if we're arguing in a rational way or in a logical way, we should, and if we're using truth-preserving rules of inference, in other words, if every step of the argument is justified by some rule of logic or some law of thought, then we should never be able to get from a sound proposition to an unsound one, or from a valid argument to an invalid conclusion. And this is why people scratch their heads. So a paradox arises clearly because of some flaw in at least one of our premises, or an error in at least one of the background assumptions supporting our premises. So we make a mistake. Paradoxes don't happen by themselves. Paradoxes arise because somewhere in our own thinking, in our own reasoning, we've smuggled in a mistake, or we've simply made a mistake, and we didn't see it. And that is always what leads to the seemingly paradoxical conclusion. So the real challenge of a paradox is to identify the error and correct it. And that's how a paradox, indeed, as Denise asserted in the chat room, can be resolved. Yes, but sometimes that's easier said than done. We do pay a price, though, when we resolve a paradox, because if and when we identify the error in our thinking and correct it, then the paradox is resolved. There's no more a problematic conclusion. It will be changed. But the price we pay for doing that, it usually necessitates some change in our common sense or taken for granted understandings of things, because it's our quote-unquote common sense understanding of things that entailed the fatal flaw to begin with. And that's what led to the paradoxical conclusion. So whenever we resolve a paradox, and we always want to do that for the sake of deepening our understanding, but we will still pay this price. It's not a bad price. It's a good thing, but we will have to change something in our previous thinking about the nature of whatever it was we were investigating in order to support the identification of the error that led to the paradox in the first place. So is this clear to everybody before I then give you some examples of paradoxes? That's the general characterization of what makes a paradox, and also the sort of price we have to pay, or if you like, the transaction cost of resolving one. They are resolvable, but we will pay a price, okay? So is everyone all right with that? Yes? Yeah, okay. So if you're all right with that, then let's have a look at some examples. Before we get to Zeno, I'm going to give you just a couple, and I'm sure you'll see immediately that not every paradox is resolvable. The first one's a computational paradox, and afterward I'll tell you why. I mean, I think it's computational. But if you look at these two sentences, sentence one asserts the following sentence is true, and sentence two asserts that the preceding sentence is false. Now, we would like to believe in general that every declarative sentence or every proposition or every copulative kind of proposition like this is either true or false. In other words, everything that we declare or propose that is in this form would be either true or false. That's what Aristotle wanted to be the case, and logicians would definitely be happier if only it were the case that every declaration is either true or false. But it's not that simple, because this pair will turn out to be basically a mutually contradicting pair that leads us into an infinite regress if we try to answer the question, is sentence one true or false? So just bear with it now. Look at sentence one. It says that the following sentence is true. And we assume that sentence one is either true or false, right? We make that assumption. So let's say it's true. Suppose for a moment that sentence one is true. If sentence one is true, then is sentence two true or false? Somebody could say. If sentence one is true, is sentence two true or false? Anyone? Sentence one is true. Sentence one asserts that sentence two is true. So if sentence one is true, then sentence two must be what? Anybody there?
False.
No. Sentence one, we're assuming sentence one is true. what does sentence 1 say about sentence 2?
That it's false.
No. Sentence 1 says the following sentence is true.
So sentence 2 is true because
Yes, sentence 1 says that sentence 2 is true, right?
Yeah.
Okay? Are you with me so far? Don't get lost yet. It's too soon. Okay? If sentence 1 is true, then sentence 2 is what? True or false?
It's true.
Of course it's true, because that's what sentence 1 says. Okay. So now let's continue. So if sentence 2 is true, but what is sentence 2 saying? Sentence 2 is saying that the preceding sentence is false. Right? So if sentence 2 is true, then what is it saying about sentence 1?
That is false.
That's right. So now we've just assumed that sentence 1 is true, but that assumption led to the conclusion that it's false. So that's a paradox, isn't it? Because it can't be both true and false at the same time, correct? Are you all lost now, or do you see the problem?
No, I see.
Good. Okay. So now let's finish. We're not finished yet. Because if sentence 1 is true, well, that leads to the conclusion that it's actually false. But then we have to take this other track. So suppose now that sentence 1 is false. So if sentence 1 is false, and sentence 1 asserts that the following sentence is true, if sentence 1 is false, then is sentence 2 true or false?
Under that assumption,
yeah,
sentence 1 is true.
Under the assumption that sentence 1 is false, then is sentence 2 true or false?
It's true.
No.
I mean, it's false.
Yes, you have to. There's a big difference. If sentence 1 is false,
sentence 1.
right? If sentence 1 is false, then sentence 2 is false, right? Because if it's not the case that sentence 2 is true, it must be the case that sentence 2 is false. But if sentence 2 is false, so it's not the case that the preceding sentence is false, then what is sentence 1? True or false?
True.
True. Good. So that means we've now assumed that sentence 1 is false, but it leads to the conclusion that sentence 1 is true. So there's no way out of this, because if we assume sentence 1 is true, then the argument shows that it's false, and if we assume sentence 1 is false, then the argument shows that it's true. This is a genuine paradox from a computational point of view. Why? Because if you program your computers to solve this problem, and you ask it whether sentence 1 is true or false, what's your computer going to do? Does anybody know?
An error.
An error.
No, it's not going to give you an error. If you program it to answer this question, you won't get an error. You'll get something worse than an error. You could try. I wouldn't try this at home, but you can do it. It's okay. You can do it with any computer language. If you program your computer to answer this question, is either of these sentences true or false? But give it a specific question: is sentence 1 true? What it will do is it will do what we've just done. It will go into a tight infinite loop. It will continue to compute that if sentence 1 is true, then sentence 1 is false, and if sentence 1 is false, then sentence 1 is true. And it will just do that until it burns itself out. It will do this until the universe ends, or until a part fails, or until the power supply needs to be replaced, or until it runs out of memory, but it will just keep cycling in that tight infinite loop. It will never come to an answer, and will never exit the program, because it can't. Do you understand this? It's called an infinite regress. It's one of many forms that an infinite regress can take. Huh? Is that clear?
Yes.
Because it'll just do what we've just done, but it'll do it very, very much more quickly, and it will be able to make millions of computations a second, but it will be stuck in the same loop. It will never be able to come to a definitive answer about whether sentence 1 is true. Okay? So that's a paradox. And that's not resolvable. You may ask, how does this arise? We have a general explanation for how such things arise, and we'll come to that in a moment. Related to this, somewhat related to this, is a very famous logical paradox. It's often called the liar paradox, and there are many, many, many variations. And in a certain way, it boils the problem embedded in the computational paradox into one sentence only. But it's an utterance, and someone is saying, "I am lying to you." So now the question is that true or false? If someone says, "Well, there you go," we have both an assertion that it's true and an assertion that it's false. This is great. Well, if someone says, "I am lying to you," if it's true that they're lying to you, then they're not lying to you, right?
So is it both?
Well, or on the other hand, if it's false, if they're really not lying to you, and if they're lying to you, then it can't be possible that they're lying to you because they're lying to you.
Unless they're lying to you even when they say the truth, or they're saying the truth even when they're lying.
Well, there you go. So is it true or false? Well, again, we can't determine this, right? Because if they're telling the truth, they're lying, and if they're not lying, then if they're telling the truth, they're lying, and if they're lying, they're telling the truth. So again, the liar paradox is not strictly resolvable. The real question for us with a paradox is why are we arriving at a paradox? And I think the third example of a set theoretic paradox will give us a clue as to why all these kinds of problems arise for us. But this one is kind of cute, and you have to imagine a village barber, okay? Imagine a village with only one barber, and the barber shaves everybody who doesn't shave himself. Is that clear? So if you don't shave yourself, it means the barber shaves you, right? But if you do shave yourself, then the barber doesn't shave you. Is that fair enough to begin with? Either you shave yourself or you go to the barber for a shave. Fair enough? That's not paradoxical, right? You with me?
Yes.
So far, so good. Right? So far, so good. There's no problem there. Either the barber shaves you. If you don't shave yourself, the barber shaves you, or you shave yourself, in which case the barber doesn't shave you. That's not paradoxical, and it's not a problem until we ask the following question. Does the barber shave himself? Now we have a paradox. Because remember, the barber shaves everybody who doesn't shave himself. So, does the barber shave himself? Well, if the barber shaves himself, then he doesn't shave himself, because he shaves everybody who doesn't shave himself. So if he shaves himself, then he doesn't shave himself. But on the other hand, if he doesn't shave himself, then he does. Because, of course, the barber shaves everyone who doesn't shave himself. So if he doesn't shave himself, it means that he shaves himself.
Isn't it when he shaves himself, he's not the barber, he's being himself?
Well, now that's a nice try to get out of the... You're trying to weasel your way out of this, but I mean, strictly speaking, he's still the barber, right? So even when he's at home, I mean, he's still the barber. So if the barber shaves himself, then he doesn't shave himself. Because he shaves those who don't shave themselves, but if he doesn't shave himself, then he has to shave himself because he shaves everyone who doesn't. So this becomes a problem, and it's only a problem, you see, when we include the barber in the set of village members. You're absolutely on the right track. I don't know who just said that, if it was Denise or somebody else, but that points exactly. It's a very nice intuition or a very nice insight, because you pointed the way to what is problematic with that setup. As long as we don't include the barber in the set of people to whom this condition applies, we're fine. So if we exclude the barber from the set of villagers, then we have no problem. Logically, the barber will either shave you if you don't shave yourself, or won't shave you if you do. So we have two sets of people, if you like. We have a subset of people, a subset of people who are shaved by the barber, and another subset of people who are not shaved by the barber because they shave themselves, and the union of those two subsets is the set of all villagers, the barber excluded. But as soon as we include the barber in in that set. Then we ask which subset does the barber belong to. Then we have the paradox, which is also not resolvable, because it's obviously impossible that if he shaves himself, he doesn't, and that if he doesn't shave himself, he does. This is meant to be a kind of amusing little sort of a problem, but it illustrates something that's actually extremely important about set theory. I won't go beyond this, but we generally think of a set as a collection of objects, which is what it is, and we generally would like to think that a set is somewhat arbitrary in the sense that we can add or delete members from the set. If you are collecting stamps, it's pretty arbitrary which stamps you want to collect or don't collect, or if you're beach combing, if you want to pick up seashells on the beach, which shells do you want to add to your collection and which shells do you not want to add. You would think, sort of in a common sense way, that the members of a set or a collection are somewhat arbitrarily assembled, but it turns out not to be the case, because if we arbitrarily want to include the barber in the set of people implicated in this allegory, then we're going to have this paradox. So it turns out that in order for set theory to be consistent, we cannot simply arbitrarily assemble different sets and expect them to work well. So this poses deeper problems if you're interested in that, in the foundations of logic and set theory. But that's just an example of something that can happen. So these paradoxes all have something in common, actually, and that is that they contain statements that are self-referential. You notice that the set of sentences 1 and 2, returning to the computational problem, they're implicating each other, right? They're not standalone sentences, because each sentence is implicating the other sentence. So there's self-referentiality going on within that set, and that is what leads to a problem. Similarly, the liar paradox is self-referential, because it's referring to a lie that it itself is in the process of telling. And so it's self-referential in the most obvious way. And it is from the self-referentiality that the actual paradox arises. And similarly, when we get to the barber, we're fine if we exclude the barber from the set of people under consideration, but as soon as we throw the barber into the mix, then the barber is also caught up in this self-referential problem, right? If shaving everyone who doesn't shave himself, if we ask about the barber, it's then self-referential. And so another paradox emerges there. But I'm suggesting that they're all related in this way, and that if we avoid self-referentiality, then we can certainly avoid a whole bunch of paradoxes, or we can try to resolve them, by imposing certain conditions on them. But you can look those up if you want to. Those are some classic paradoxes in the philosophy of logic and set theory. But I want to go to Zeno, because Zeno's paradoxes are actually partly empirical, because they're grounded in what we would think about as everyday experience. Okay? Now, I'm glad that one of you was laughing. I assume, Jonette, you're laughing at the barber example. Yeah, it's supposed to be amusing. And also at the same time, it is obviously paradoxical. Okay, so everybody clear about something about the nature of some of these paradoxes and how we get ourselves into trouble, perhaps by composing self-referential kinds of sentences at times? All right. So now we go to Zeno of Elea. Zeno was a common name back then. Zeno, Z-E-N-O, okay? It was a common name back in the day among the Greeks, and there's a few different Zenos rattling around. But this particular Zeno formulated 4 paradoxes of motion. And what he was really great, because he came up with these thought experiments that essentially demonstrate the common denominator in all his paradoxes is that everyday motion, as we normally conceive it and experience it, is somehow impossible. That we can't do, in some sense, or we cannot explain how it is that we do what we appear to be doing when we move from one place to another, or when an object moves from one place to another. And it's making us think much more carefully about the nature of motion, the nature of space and time, and how objects traverse trajectories across space and time. And there's some very deeply puzzling things that come out of Zeno's paradoxes. And it wasn't until centuries later that we actually got satisfactory resolutions to all of them, because in some cases the ancient Greeks did not have actually enough mathematical machinery to resolve them. They had geometry, and they were really great geometers, but geometry itself only reinforces the paradoxical nature of some of the things that Zeno is positing. So we needed more powerful tools of mathematical analysis that didn't emerge really until the 19th century in order to lay them fully to rest. But you don't panic. You don't need mathematical analysis to understand these problems. We can explain the resolution in ordinary language. That's what I'm going to do today, is try to use ordinary language to explain how they finally are resolved. But they're not. They're still somewhat problematic, especially the arrow paradox. We're going to do 3 of the 4. They're mentioned in your textbook, and if you look online, you'll see great treatments of them. The Stanford Encyclopedia does a really good job, and there are many, many other treatments of Zeno's paradoxes. But we're going to take the first one first. It's the simplest one, and it's called the dilemma. The dichotomy paradox, not the dilemma. Strike that. The dichotomy paradox. And the dichotomy paradox, I can just describe it to you, and in very simply, that is, the dichotomy paradox says that basically a runner can never finish a race. Why can't a runner ever finish a race? Or for that matter, you could never walk out of the room that you're in. If you want to leave the room and go to the next room, the dichotomy paradox purports to demonstrate that that's impossible. And what's the argument? Well, the argument is as follows. If we think about a runner, all right, a runner running a race, let's say it's a 100-meter sprint, okay? So Zeno would say, well, the runner can never finish the race. Why? As follows. For the runner to finish the race, and I want you to hit a button when you tell me what's wrong, okay? As soon as if I say something that's wrong or something that sounds impossible or flawed, I want you to push the button and tell me, and then we'll stop. But here's Zeno's argument. In order for the runner to finish the race, the runner has to get halfway to the end first. Before you get anywhere, you have to get halfway there, correct? I mean, you can't get all the way there before you get halfway there, right? Fair enough? You have to get halfway there. And, of course, you can't get halfway there until you get a quarter of the way there. And every increment, it takes you a certain amount of time. I mean, the runner is going to take a certain amount of time to get halfway to the finish line. And, of course, before you get halfway, if you keep dividing by 2, you realize you have to get a quarter of the way, and you have to get an eighth of the way and a 16th of the way, and you can keep subdividing the distance that you have to traverse by 2 arbitrarily or by any number, but you will be able to subdivide that infinitely. There's no end to the subdivisions. But wait a second, there's the problem. If there's no end to the subdivisions, how can you possibly traverse an infinite number of subdivisions in a finite time? You can't, because if it takes you a certain amount of time to get halfway to the end, it's also going to take you a certain amount of time to get a quarter of the way. Of course, less time, but you still have to get that much before you get to the end. You get to get halfway. Before you get halfway, you have to get a quarter of the way. Before you get a quarter of the way, you have to get an eighth of the way, then a 16th, then a 32nd, then a 64th, and so on ad infinitum. You can infinitely subdivide by 2. 1 over 2 to the nth power, you keep making those subdivisions, but every time you make a subdivision, you need another chunk of time to complete it. And if there's an infinite number of subdivisions, then there obviously is an infinite number of time required. So you can never finish the race because you don't have an infinite number of time. And that's Zeno's argument. Therefore, you can't get to the finish line. Now, we all know that everybody gets to the finish line sooner or later. But then what's wrong with Zeno's argument? That's the paradox. Where is Zeno going wrong? Where is Zeno's argument flawed? You get the argument first, then we'll try to dissect it and arrive at what's problematic. And there are several possibilities. But do you all understand the problem? Is everybody okay, at least with what Zeno's telling us? Yeah?
Yeah.
Now you all know that that's crazy in some way, because we can all leave the room, but the same argument applies, right? If you want to leave the room, then Zeno would say, well, you have to get halfway. If I say Zeno, it's because I'm speaking British English, and in the US we'd say Zeno. But I mean, I'm bilingual, so sometimes I say Zeno and sometimes I say Zeno. So I'm referring to the same guy, okay? Just like a zebra and zebra, right? In the US, we say zebra, and in the UK, they say zebra. So when I get to the Z's, I sometimes lapse into bilingual English. So just understand, whether I say Zeno or Zeno, it's the same guy, okay? So Zeno would say, if you want to leave the room, you have to get halfway there. You can't get to the door till you get halfway to the door. You want to get halfway to the door, but before you get halfway to the door, you get a quarter way to the door. It's the same argument. You have to get a quarter of the way to the door, and an eighth of the way, and so forth. So you have to traverse an infinite number of intervals, right? An infinite number of intervals, and each interval that you traverse takes you a certain amount of time, and you can't possibly do this because you don't have an infinite amount of time. So how do you ever get to the door? You can't. Or for that matter, you'd have to take an infinite number of steps, actually. Right? You can't do that. So how do you ever leave the room? Now, we all know we leave the room, just as we know that runners finish races. But then the question, the more challenging part of this, is to identify, where is Zeno going wrong? How does he manage to conclude that we can't traverse a finite distance because it takes an infinite number of intervals, right? All right, I'm sure none of you have ever lost sleep over this. Aristotle was the first one to try to refute Zeno's paradoxes. Aristotle came up with solutions, and many other philosophers have come up with different ways of resolving this. I think that ultimately there is a way to resolve it, but again, it will require that we modify some of our common sense understanding about the nature of space and time too. Later, time will get implicated, but really this is about space, about traversing spatial dimensions. So does anybody have any idea what might be wrong when you start where you end? Well, I'm not sure, Randy, if we start where we end. I mean, we start at the beginning of a race and we reach the finish line, and no one is asserting that the finish line and the starting line are in the same place. They're separated by whatever the length of the race is. So I'm not sure that it's the case that we start where we finish. We start in one place, we finish in another. Zeno's challenge is, how do we ever get there, given that we have to traverse an infinite number of subdivisions of space in order to do it. And if each subdivision of space takes a certain finite time, but there are an infinite number of subdivisions, then we must need an infinite amount of time to do it. And we don't have that. So how do we do it? Any other ideas? Well, they're meant to be baffling. These problems are meant to challenge very serious thinkers and to make us think more deeply about the nature of things. So let me give you a simple solution, and then we'll tackle, I think, not a more difficult, but a more nuanced solution, which is also quite revealing. We have a comment from Matthias. One step per division. Interesting. That's a very good analysis. Am I pronouncing your name correctly? Matthias or Matthias? That's very good. Doesn't that assume you take one step per division? Not necessarily. As the divisions get smaller, we would need to take smaller and smaller steps, right? As the distance infinitely gets lower, the time it takes would be infinitely lower. Well, unnoticeable is not the issue. The question is, Zeno's question is, if there's an infinite number of steps that we have to take, and each step takes a finite amount of time, then we would need an infinite amount of time to traverse the distance. So does this mean that one step would beat infinity according to the paradox? Well, solution A actually tells us something else. And solution A is as follows: that if you take the series 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus ... 1 over 2 to the nth power, that series converges. So even though it's an infinite series, it turns out to have a finite sum. Okay, so not every infinite collection of terms has an infinite sum. Okay, so actually, this is it's called a convergent series, and so it turns out that the sum of that series is actually 1. A half plus an eighth, a half plus a quarter plus an eighth plus a 16th. It's very easy to prove. I'm not going to do the math. We could do all this without math, and I'm not doing any math with you, but you can look it up. It's a very, very simple proof. Just high school algebra is all you need. You don't need anything more to prove that the sum, if S is equal to, I'll type it in, 1/2, right, plus 1/4 plus 1/8 plus ... right, 1 over 2 to the, I'm looking for the upside down caret, 1 plus 2 to the 1 plus n to the 2. That's the series, right? Hang on while I just type it in. That's the infinite series. And it turns out that that actually has a finite sum. S is actually equal to 1. Believe it or not, if you take all the terms and add them up, the more terms you take, the closer you get to 1. And so that means that actually you could traverse that in a finite amount of time, even though it's an infinite number of steps. The series converges, and so it has a finite sum. And so if you add up all the amounts of time, the ever smaller chunks of time you need, even though it's an infinite number of steps, you actually could take them in a finite amount of time. So if you look at the paradox from the point of view of the clock running, you'll be able to finish. You'll be able to actually get to the finish line in a finite amount of time. So that's one way of attacking Zeno's assumption. And the flaw in that line of reasoning, if you look at the paradox on the time axis, the flaw in the reasoning is that it takes an infinite amount of time to take an infinite number of steps. And it actually doesn't if the series converges to a finite sum. So that's one way to get around the problem. The spatial analysis of it may be simpler for you. Those of you who have not encountered things like convergent series, if you've done calculus, you already know this. But the spatial analysis is actually quite interesting. And here's the way of understanding it in spatial terms. I'm going to draw a little picture on the whiteboard, and I think that'll make it absolutely clear to all of you where the flaw, or where the sort of conceptual error, which Zeno may have deliberately built into this, right? He knows, like everybody else, that you can leave the room or you can finish a race, but he's challenging us to explain something that really hadn't been thought about before. And so here is what I want now to present to you, just a little kind of a drawing. If I can find the where do I get the remind me, where do I get the whiteboard here? It's been a while since I've used it. Anybody? More.
You can use share screen, and then one of the options should be whiteboard.
It should be. I agree with you. But I'm not. Ah, there it is. Thank you very much. It was hiding in plain sight. Right. Okay. Whiteboard. Here we go. Thank you very much. So here's the thing. Suppose that we take a line segment. Do they have a line segment? Yeah, they do. Here's a line. So let me ask you this question, okay? There's a line, right? And now there's a longer line, okay? And there's a longer line, right? So suppose we need to walk these distances. So let's say this is 1 step, and let's say this is 2 steps, and let's say this is 3 steps, right? It's not the scale, but close enough. So that's 1 step, that's 2 steps, that's 3 steps. So what Zeno is saying is that you could never even take 1 step because this line contains, how many points are on this line, by the way? How many points are on the line?
2.
Anybody?
Would it be 1?
1 point? No. A point is like a pencil point, right? A point is, you see, if you understand geometry, and this is the solution in geometric terms, which puzzled the Greeks because they understood geometry, a line is defined as a projection of points in a given direction. A point is something that has position but no magnitude. So a point is that's why you sharpen your pencil when you're doing geometry. A point should be a tiny little thing. It actually doesn't have any dimension at all. It's too small. It has no dimension, but it has a place, it has a location, and if you project that point in a given direction, that's what a straight line is made of. It's made of a projection of points. So how many points are on that line?
Yeah.
I'm sorry, I can't hear you.
The part of the place.
I still can't hear you.
The end of it.
I don't. I'm sorry. Infinite. Randy said infinite. I can't hear
Okay.
some of you because your mics are not working. But one of you, Randy, typed in infinite. No, it's not unknown, Denise. It is known, and Randy has the answer. Every one of these lines contains an infinite number of points. Okay? So the number of points, this is the thing, all right? The length of these lines, the lengths of these lines are different, correct? Obviously, if you measure them with a ruler, the lengths of these lines are different. But they each contain an infinite number of points. That's rather shocking, actually, if you think about it. So, do you understand how this informs Zeno's paradox? What Zeno was trying to tell us is that you can't walk from one end of the line to the other because you have to take an infinite number of steps to do it. And another way of understanding that statement is that in order for you to get from the beginning of the line to the end of the line, you have to traverse each point. But since the line contains an infinite number of points, you can never take an infinite number of steps, so you can never traverse the line. But what Zeno is not saying, and which should be perfectly obvious to you, is that every time you take a step, you are traversing an infinite number of points, right? If you take 1 step and you measure that distance, let's say it's 1 foot, well, that's 1 foot in terms of the interval, right? The spatial interval you've crossed, but that interval itself contains an infinite number of points. So every time you take a step, you're traversing an infinite number of points. And it doesn't matter that one line is longer than the other. They actually all contain the same number of points. And that is the deeper and somewhat crazy truth that actually allows us to solve Zeno's problem. And this is really weird because you generally would think, wouldn't you, in common sense terms, that the longer a line is, the more points it contains? Isn't that what your kind of common sense would want to tell you? Right? That, you know, a line that's twice as long as another line must contain twice as many points? Oh, if that's what you said, Matthias, then that's exactly right. But you see that if every line contains the same number of points, then the number of points is independent of the length. But that's exactly what we need to solve Zeno's problem. Because what we're saying to Zeno is, look, I can get to the door because the door is a finite number of steps away depending on the length of my stride. Everyone will take a certain number of strides and therefore cross that spatial interval as you measure it, whether you're measuring it in inches or feet or meters or whatever unit of measure, doesn't matter. It's definitely a finite measurable interval between the start line and the finish line. But the fact is that regardless of the actual length of the interval, every interval contains an infinite number of points. And by taking a step, we can step over an infinite number of points. So we don't have to worry about subdividing it. It's not necessary. We don't have to be concerned about how many points we're stepping over. So the fundamental distinction then is between the length of a line and how many points it contains. And Zeno was focused on the points. And so Zeno was saying, well, because we have an infinite number of points, we can never count them all. We can never, basically step over them all, so we can never traverse the interval. But that's not true. We can traverse an interval without worrying about how many points it contains. Is this clear to you? Are some of you lost? Or is this clear? Somewhat. All right. Well, I need you to think about it. And here's the thing. I don't know how to delete this. I guess there's an eraser, but I'll end up erasing. Yeah, okay. So here's the proof. If you want to convince yourselves that every line contains the same number of points, this is what you can do. You can draw a triangle. You can do this at home. I'm not drawing it very well, but here you go, okay? So I have 3 lines of different lengths, right? There's line A. There's line B. And there's line C. Correct? Now, A, B, and C are all different lengths. Obviously, line A is shorter, line B is longer, line C is longest. But if you now start connecting the points together, this is what you're going to arrive at. I don't know how to change the color. I'd like to do that. But anyway, suppose we start drawing a line now from the vertex to the base. Do you notice that every line we draw from the vertex to the base picks out a single point on A, B, and C, right? There's a single set of points that are identified each time we draw a line. Do you see this? Every line we draw from the vertex to the base picks out exactly one point on each line uniquely. So each time we draw a line from the vertex to the base, we're picking out one set of unique points on line A, B, and C, right? 1 point on A corresponds to 1 point on B, corresponds to 1 point on C. If we draw all possible lines from the vertex to the base, we're actually going to ultimately include every possible set of points on each line, A, B, and C, and therefore we're going to not miss any, if you imagine this, and therefore line A, line B, and line C will be shown each to contain the same number of points, even though line A is shorter than line B and line B is shorter than line C. They all contain the same number of points. Now that's pretty mind-blowing, because our normal kind of intuition would probably inform us that the longer the line is, the more points it contains, but that's not the case. And that is, I think, the deeper answer to Zeno's dichotomy problem, that we can traverse an interval without worrying about the infinity of points that we're necessarily traversing in the process. All right? Is that fair enough? I know you might want to think about this, and all's well if you do, because this is a long-standing paradox. And although it has been resolved, you're hearing it for the first time, and you need to spend some time with it. The second one, however, we're going to now cover the Achilles and the tortoise. And the second one is similar, but it's a little more mind-blowing. Okay, I'm going to leave this one here. And we have 2 more to cover. I'm going to cover Achilles and the tortoise this morning. And then on Thursday in my breakout lecture with section M, I'm going to cover the arrow paradox. Don't try this at home. The arrow paradox it says that an arrow that's shot from a bow can never move. It's the most interesting of the four. We'll cover it on Thursday, but right now I want to cover one that's completely counterintuitive. It says, Achilles is by repute, by myth, a very fast runner. Yes, Achilles is extremely swift. It's like he's faster than Usain Bolt. He's the fastest runner ever. And the tortoise we know to be very slow. Tortoises are very slow moving. They're long lived, mind you, but they're very slow moving creatures. And Zeno sets up this delightful problem of a race between Achilles and the tortoise. And what he's going to show us in a minute is that if you give the tortoise a head start, as long as you give the tortoise a head start, Achilles could never catch the tortoise. Okay, and the race, is of finite length, but there's enough time for Achilles to catch the tortoise, but it doesn't matter. If you give the tortoise a head start, Achilles will never be able to catch the tortoise. That's Zeno's second paradox. Let's look at a picture that illustrates it. I know that sounds crazy to us, right? Of course it sounds crazy. It should sound crazy because we know that Achilles can catch the tortoise eventually. Nonetheless, according to Zeno, he can't. So here's the problem. I'll just load this up for you so you can see a diagram of this paradox. Let me share the screen again. And here's the runner. Okay, so you can all see this. And that's meant to be Achilles. Okay? And the tortoise is the tortoise. Now, here's the thing. That what we do is we give the tortoise a head start. So Achilles starts at point A on the screen. And we don't let him start yet. First, we let the tortoise get from point A to point B. So the tortoise, let's say, has a 10-meter head start. It doesn't matter what the actual distance is. It's arbitrary, but we'll say the tortoise gets a 10-meter head start. Okay? It could be any distance. You don't have to attach a number to it. We know. We gave the tortoise a head start, and then when the tortoise got a certain distance, we said to Achilles, okay, you could start running. So here's Zeno's argument, or Zeno's argument. It's really quite clever. Zeno says, all right, now Achilles is much quicker. So by the time Achilles gets to point B, where the tortoise was, he's going to do that at a quicker time than the tortoise did. But nonetheless, by the time Achilles gets to where the tortoise was, at point B, we'll call it A prime, the tortoise has still moved a little further ahead, right? Because, remember, the tortoise is running the whole time, although Achilles is running faster. So as long as the tortoise gets that head start, by the time Achilles gets to where the tortoise was, when Achilles started running, the tortoise has moved a little further down. Not much, but a little further down. So that by the time Achilles gets to A prime, the tortoise is now at B prime. It's still a little further ahead. Of course, Achilles will make up that distance even quicker because it's a shorter distance. But nonetheless, by the time Achilles gets there, which is A double prime, the tortoise is still a little bit further ahead, less and less ahead every time we track this, but the tortoise is still ahead of Achilles. And every time Achilles gets to B double, if Achilles gets to, to B double prime, we call it A triple prime, the tortoise will be a little further ahead at B triple prime and ad infinitum. So no matter how much Achilles tries to catch up to the tortoise, every time Achilles gets to where the tortoise was, the tortoise is always going to be a little bit further ahead, incrementally by less and less. But there's no point at which Achilles can actually ever catch the tortoise. And that's the argument. So Achilles can never catch the tortoise. As long as the tortoise gets a head start, no way can Achilles catch the tortoise. Now, you know that that's not true, right? But isn't that a clever argument? What's wrong with the argument? Yeah, every time the tortoise gets a head start, Achilles, tortoise gets, my hands are reversed here. So anyway, tortoise gets a head start, Achilles gets to that point, but the tortoise is a little further ahead by the time he gets there. So now Achilles catches him very quickly, but the tortoise is a little further ahead. Achilles gets to that point, tortoise is less ahead, that point, less ahead, incrementally shrinking all the time, but there's never a point at which Achilles actually can catch the tortoise. So it's paradoxical, because our common sense tells us that, of course, at some point Achilles is going to go past the tortoise. So what's wrong with Zeno's argument? Where's the flaw? Any ideas? This is much more difficult. This is a much more difficult problem. And I wouldn't be surprised if you're stumped. Not so easy to explain this one. Very clever for Zeno to come up with it, but by no means is it trivial. No means at all. Of course, it's not true. But again, the challenge of a paradox is to explain where the reasoning goes astray. Yeah. So let me give you a hint. I hear you're all thinking. I'm glad you're all thinking. Okay, Matthias, wasn't he just go ahead and make up for the distance we know the tortoise will make? Well, this is Zeno's argument. They're all moving at a constant rate. They're not accelerating, Matthias. We're assuming that they're running at a constant speed. Once, they take a step, they're up to constant speed. So, but if they're at constant speed, then Achilles is never going to catch him, because every time Achilles gets to where the tortoise was, the tortoise is a little further ahead. Although that distance is shrinking all the time. All that time. So yeah, that's a good idea, but this is not the condition of the actual argument. They're both going at a constant rate. Achilles starts later than the tortoise.
If they're going on a constant rate, then the tortoise is always going to win, because the tortoise had a head start from Achilles.
No, because Achilles' constant rate is much quicker than the tortoise's constant rate. So we know our common sense tells us that even though the tortoise has a head start, that Achilles' speed is much faster. If you're driving at 10 miles an hour and somebody else is driving at 50 miles an hour, they're going to catch you, even if you have a head start. You're a constant rate.
When you say a constant rate, it could actually mean anything, because it could mean 0, it could mean 10 miles an hour, unless you specify which one is actually going at each one of them actually goes at a constant rate. Yeah, so for instance, like the tortoise going at 5 miles an hour, and then Achilles is going at 10 miles an hour. Therefore, in that particular condition, then Achilles will actually win.
Well, this is the thing. You have to understand something, that you got to free yourself up from numbers. This problem has nothing to do with the actual speed of the tortoise or the speed of Achilles. It's got nothing to do with their actual rates. The assumption is, as you say, and it's very important that you say it, they are going at constant rates. The rate of Achilles is much faster than the rate of the tortoise. So that's all the information we need to know, that if the race goes on long enough, Achilles is bound to overtake the tortoise because he runs faster. Okay? It doesn't matter what the actual measurement is. We're just saying if the runner is faster than the tortoise, then we know that the runner is eventually going to overtake the tortoise, and it doesn't matter how much the head start is. We understand that. But what we're not able to do so far is to explain what's wrong with Zeno's reasoning. Zeno's reasoning is that it can never happen, because no matter where the tortoise is, when Achilles gets there, it's always a little further ahead, because it always had a head start. Even though it's going to get incrementally less and less ahead, still always going to be ahead, because whenever Achilles gets to where the tortoise was, the tortoise is a little further ahead again. And so it's got nothing to do with the actual rate of speed. If you know the rate of speed and you know the time of the head start, you can always calculate exactly when they will meet, when Achilles, at the moment when Achilles will overtake the tortoise and go ahead. That's not Zeno's problem. Zeno's problem is, how does it ever catch up to him? And this is where the tortoise and the hare, yeah, probably. Well, there you go. At Maisha, of course, at some point they will intersect. This is what our common sense tells us, that if you're going faster than somebody and you overtake them, right, then at a certain point in time, you're going to be at exactly the same place, right? You're behind for a certain amount of time, and then at one moment only, at one point in time, you're exactly in the same place, and then you go ahead and you remain ahead. That's what our common sense and our life experience tells us. But we're still not giving Zeno the answer he's demanding. which is how does it ever happen that that point arrives where they actually intersect. But now you're on the right track, Maisha. To ask that question is the key insight. And then we have to go back to Zeno, who's saying they can never intersect. You're exactly on the right track by realizing this, that before Achilles goes ahead, he has to pull level with the tortoise. And how does he ever pull level with the tortoise if the tortoise got a head start, and then by the time he's there, the tortoise is there. By the time he's there, the tortoise is there. By the time he's there, the tortoise is there. How does he ever pull level? Here's the way to resolve it. It's something that is so simple, and yet it's mind-boggling at the same time. What Zeno is showing us, and I'll say it in English, and I'll type it on the whiteboard. Zeno is not showing us that the tortoise can never be caught by Achilles. Zeno is very clever. He may have known this. What Zeno is showing us is something different. And this is what you need to get, okay? How do I erase this? There, clear. All right, so here is what Zeno is demonstrating. Zeno is showing that there is no last instant. You should write this down or track it. You know, Zeno is showing something very important. It's not that Achilles can never catch a tortoise, however. It's really a cute trick. Zeno is really showing that there is no last instant at which Achilles fails to overtake the tortoise. This is what Zeno is proving with his argument. There is no final instant at which Achilles fails to overtake the tortoise. But this, and back to Maisha's insight, this does not prove however, that there is no first instant at which Achilles succeeds in overtaking the tortoise. Now, you may need to think about this. It is not obvious by any means. That's why the paradox was with us for so many centuries. This was really not made clear for many centuries. Zeno is showing what his argument, as I've related it to you, as the classical accounts relate to you, is that there's no last instant at which Achilles fails to overtake the tortoise. He gets closer and closer and closer, but there's no point at which it's the last moment where he fails to overtake the tortoise. That, however, does not prove that there's no first instant at which he succeeds. And of course, as Maisha said, there's going to be some point at which he draws level. Zeno's avoiding that whole situation. Zeno's just showing that there's no last instant at which he fails. Let me ask you in a different way the same question, and then you'll maybe get this right away. I hope some of you will. Suppose I ask this. What is the last number before the number 1? Let's say we're going from 0 to 1 in the real number line, okay? So what's the last number we get to before we get to number 1? Anybody? If we're going from 0 to 1, what's the last number? The last number, I'm going to go to the chat room. No, not 0, Denise. Denise, we're going from 0 to 1. Imagine this.
Is it infinite?
No. Don't get mixed up now. Just let me draw the picture. Okay, this is a number line. And this is, we started arbitrarily. We start this line at 0. And arbitrarily, we end this line at 1. Okay? That's a number line, going from 0 to 1. Now, I'm asking you, what's the last number on that line before 1? Not 1 point, Javier, not 1.9. That's off the line, right? 0.999. Okay, so when we get close to 1, we get to 0.999, right? Okay, but that's not the last number, right? Because between 0.99 and 1, there is what? 0.9999, right? So we're closer to 1, but we're not there yet. And then there's 0.999. 99999, right? But we're still not at 1, and in fact, it goes on infinitely. So there is no last number before the number 1, correct? It is infinite, Cesar. Correct. There is no final number before we get to the number 1. You get this? Just never mind Zeno for a moment. Just process this. There is no final number. We'll get closer and closer to 1, but never to 1. No, it doesn't mean we never get to 1. It just means that there is no last number before we get to 1. 1 is there. It's been there the whole time. And that is the resolution to Zeno's paradox of Achilles and the tortoise. There is no final instant at which Achilles fails to overtake the tortoise, just like in exactly the same way as there is no final number just before we get to the number 1, but that doesn't mean that there isn't a number 1. If there were no final number, if there were no, the fact that there's no final number before the number 1 doesn't mean that there is no number 1. And the fact that there's no last instant at which Achilles fails to overtake the tortoise does not prove that there's no first instant at which he succeeds. And that was exactly what Maisha was saying. But wait a second, no matter how many times he fails to overtake the tortoise, which is actually an infinite number of times, an infinite number of instants will exist at which Achilles fails to overtake the tortoise. That's what Zeno is illustrating. But that does not prove that there is no first instant at which he succeeds. Of course there is. And when they reach that number 1, right, that's the first instant at which he succeeds. And after that, he'll always be ahead of the tortoise. But by the same token, there's no first instance at which he'll be ahead of the tortoise either. Isn't that interesting? I mean, Zeno didn't go that far, but we can flip the problem and say, yeah, but after they draw level, there's no first instant at which he goes ahead either. There's an infinite number of instants at which he will go ahead and no first one. Zeno could have said, therefore, he could never go ahead. It would have been the same fallacy on the other side of the point of intersection. He left it alone, maybe just as well for all of us. I'm going to leave it there with you. Those are the first 2 paradoxes of Zeno, and this resolution is a little more complex than the dichotomy problem, but I hope you realize the point. The point is that the tortoise will indeed, Achilles rather, will indeed fail to overtake the tortoise at an infinite number of points, but that doesn't mean that there's no instant at which he will not draw level with him. And of course he will, and of course he'll overtake him. Okay? I hope that that's clear to you. But I also hope you see that Zeno's paradoxes are not trivial, even though they seem obviously wrong on their face, and they contradict our everyday experience. Trying to understand the flaw in the actual argument is by no means trivial. Okay? So I will see some of you again on Thursday, and we'll look at the arrow paradox at that point, which is even harder. I think it's just as obviously false. It says that if you shoot an arrow from a bow, the arrow can't go anywhere. So like you shoot an arrow, but it can't possibly fly through the air. That's why I'm saying don't try this at home, okay? Because our common sense experience tells us that if you shoot an arrow from a bow, it definitely travels through the air. But Zeno has a very clever argument to show that the arrow can't possibly move. And we'll look at that on Thursday in my group, and I hope you'll look at that argument in your breakout lectures, okay? So have a wonderful day. Don't lose any sleep over this, but I hope you get intrigued by some of these problems. And we're going to explore a whole variety of paradoxes as we go along, okay? So have a wonderful day, everybody. Be safe and well. And we'll resume Zeno, and you'll resume Zeno this week. Take care, and I'll stop the recording here.